the invisible architecture, our place in a universe of dark matter and distant suns. Look up at the night sky. For millennia, it has been our canvas for myths, our map for navigation, our clock for seasons. But above all, it has been a mirror reflecting our deepest questions. Are we alone? Where did all of this come from? And what is our place within this vast, silent expanse? For most of human history, these questions were the domain of philosophers and poets. Our home, the Earth, seemed to be the center of everything, a unique, privileged stage for the drama of life. But a revolution in our understanding, a journey of discovery that continues to this day, has shattered that illusion. We've come to realize that our world is but one of countless others, adrift in a cosmic ocean of unimaginable scale and complexity. This is the story of that journey, a story of how we are peering into the darkness between the stars, searching for worlds like our own. It's a story of the cosmic monsters that lurk in the shadows, defying our understanding of reality itself. And it is the story of our quest to read the grand cosmic narrative. From its explosive beginning to its unknown, ultimate fate, our search begins close to home. In our own solar system, we see a family of worlds, each with its own character. The searing plains of Venus, the cratered face of Mercury, the gas giants of Jupiter and Saturn with their retinue of dozens of moons. For a long time, we hoped to find neighbors here. Mars, with its polar ice caps and ancient riverbeds, was a prime candidate. It whispers of a past where liquid water flowed, a time when it might have been more like Earth, and the search continues in more surprising places. Beneath the icy crust of Jupiter's moon Europa, scientists believe a vast, saltwater ocean sloshes in the dark, kept liquid by the gravitational tug of its parent planet. The same is true for Enceladus, a tiny moon of Saturn, which actively spews geysers of water vapor into space, containing organic molecules, the very building blocks of life as we know it. These tantalizing possibilities fuel our imagination. But even these worlds are right on our doorstep. What lies beyond? Beyond the pull of our sun, in the realm of other stars. Until just a few decades ago, we had no proof that any other star hosted planets. They were simply too small, too dim, and too far away to be seen directly. But we are a clever species. If we can't see something, we learn to look for its shadow. This led to the development of the transit method. The idea is simple, yet brilliant. If a planet passes directly in front of its star from our point of view, it will block a tiny fraction of the star's light, causing a minuscule, temporary dip in its brightness. It's like watching for the shadow of a moth flying in front of a distant searchlight. By monitoring the brightness of thousands of stars continuously, we could catch these telltale winks. In 2009, NASA launched a spacecraft designed to do exactly that. Its name was Kepler. For 4 years, it stared unblinkingly at a single patch of sky in the constellation Cygnus, watching 150,000 stars for any sign of a passing world. What Kepler found started a revolution. It didn't just find a few planets. It found thousands. It revealed that planets are not a rare exception, but the common rule. Kepler's data suggests that there are more planets in our galaxy than there are stars. Rocky worlds, gas giants, super-Earths bigger than our own planet, and mini-Neptunes. A veritable zoo of worlds, most of them unlike anything in our own solar system. Suddenly, the cosmos felt a lot less empty. The question was no longer, are there other planets? But are there other Earths? To answer that, astronomers began to focus on a concept known as the habitable zone, sometimes called the Goldilocks zone. This is the orbital region around a star where the temperature is just right not too hot, not too cold for liquid water to exist on a planet's surface. Water is the solvent for life as we know it, the medium in which the complex chemistry of biology unfolds. Kepler and its successor, the TESS satellite, began to find planets squarely within these Goldilocks zones. The news was electrifying. We found planets like Kepler 186f, an Earth-sized world in the habitable zone of a cool, red dwarf star 500 light-years away. And then there was Proxima Centauri b, orbiting the very next star over from our Sun. A potentially rocky world, tantalizingly closer just over for light-years away. Perhaps the most famous of these discoveries is the TRAPPIST-1 system. Here, just 40 light-years away. An ultra-cool dwarf star hosts not one, but 7 Earth-sized rocky planets. At least 3 of them orbit within the star's habitable zone. A whole solar system of potential Earths, all clustered around their faint red sun. But finding a planet in the right place is only the first step. Is it truly habitable? A world in the Goldilocks zone could be a barren desert or a pressure cooker with a toxic runaway greenhouse atmosphere like Venus. The key to knowing the difference lies in its air. An atmosphere can reveal a planet's secrets. This is where the next great leap in our cosmic exploration comes in. The James Webb Space Telescope. Positioned 1 million miles from Earth, with a golden mirror over 21 feet across. Webb is a time machine and a cosmic chemist rolled into one. It is designed to look at the universe in infrared light, which allows it to peer through dust clouds and see the faint heat from the most distant objects. Most importantly for the search for life, Webb can perform a kind of cosmic alchemy called atmospheric spectroscopy. When a planet transits its star, a tiny amount of starlight filters through the planet's atmosphere. Different gases in that atmosphere absorb specific wavelengths or colors of light. By analyzing the starlight that reaches us, Webb can detect these missing colors, creating a barcode that tells us what the alien air is made of. We are hunting for biosignatures gases that could indicate the presence of life. Water vapor is a primary target. Methane is another, and the holy grail would be oxygen. On Earth, our oxygen-rich atmosphere is almost entirely the product of life itself, of photosynthesis by plants and cyanobacteria over billions of years. Finding oxygen in the atmosphere of a distant, rocky world would be a staggering discovery. Webb has already begun this work, successfully detecting water vapor, carbon dioxide, and even clouds in the atmospheres of exoplanets. So far, these have been giant gas planets, not terrestrial Earth-like worlds. But the technology is proven. The hunt is on. Every new observation brings us closer to potentially answering that age-old question. Yet, as we search for havens of life, our telescopes have also revealed that the universe is not an entirely gentle or welcoming place. It is a place of extremes. It forges worlds in the fiery cores of collapsing nebulae. And it hosts objects of such violence and power they almost beggar belief. At the center of galaxies, in the graveyards of dead stars, lurk the most mysterious and terrifying objects in the cosmos: black holes. A black hole is what remains when a truly massive star, at least 20 times the mass of our Sun, runs out of fuel. Its own gravity, no longer balanced by the outward push of nuclear fusion, becomes unstoppable. The star collapses in on itself, crushing matter down to an infinitely small and dense point called a singularity. Around this singularity is a boundary of no return called the event horizon. It isn't a physical surface, but a threshold. Cross the event horizon, and gravity becomes so powerful that nothing, no ship, no particle, not even light itself can escape. It is the universe's ultimate prison. For decades, black holes were purely theoretical, a strange prediction of Einstein's general theory of relativity. How could you ever prove something exists if By its very nature, it emits no light. The answer, once again, was to look for its influence for the chaos it creates in its vicinity. Astronomers notice stars at the centers of galaxies orbiting. Nothing. They whipped around an invisible point at incredible speeds, held in a gravitational dance by a partner they could not see. By tracking these orbits, astronomers could calculate the mass of the unseen object. The numbers were astronomical. At the heart of our own Milky Way, a hidden object was found to have the mass of 4 million suns, all crammed into a space smaller than the orbit of Mercury. This was Sagittarius A*, our galaxy's own supermassive black hole. We learned that there are two main classes of these monsters. The stellar mass black holes, scattered throughout the galaxy like cosmic ghosts, are the remnants of single stars. But the supermassive black holes are the titans. They are millions, or even billions, of times the mass of our Sun. And they sit at the heart of nearly every large galaxy we have ever observed, including our own. They are the gravitational anchors around which entire galaxies spin. We also learn to see the light of their victims. As gas, dust, and even entire stars get too close, they are pulled into a spiraling vortex called an accretion disk. Like water swirling down a drain, the material spins faster and faster as it nears the event horizon. Heated to millions of degrees by friction, this superheated material glows with incredible intensity, blasting out jets of energy and radiation, particularly X-rays, that can be seen from across the universe. These brilliant, active galactic centers, known as quasars, are some of the brightest objects in existence, all powered by matter on its final, desperate scream before being consumed. But the ultimate proof came not as light, but as a vibration. In 2015, an incredible experiment called LIGO, the Laser Interferometer Gravitational Wave Observatory, detected something new. It was a ripple in the very fabric of spacetime itself. These gravitational waves were the signature of a cataclysmic event a billion light-years away. The collision and merger of two stellar mass black holes. Einstein's last great prediction was confirmed. We could now hear the universe, feeling the echoes of its most violent events. The final piece of the puzzle fell into place in 2019, an international collaboration of radio telescopes. Working together as a single planet-sized instrument called the Event Horizon Telescope, achieved the impossible. They captured the first-ever direct image of a black hole's silhouette. It was not of our own Sagittarius A*, but the far larger beast at the heart of the galaxy Messier 87, a giant weighing 6.5 billion times the mass of our Sun. The image was breathtaking. It showed a ring of glowing, superheated gas orbiting a perfect circle of pure blackness. That blackness was the shadow of the black hole itself, the point of no return made visible. We were, for the first time, staring into the abyss. We had photographed the edge of reality. This quest to understand black holes and to find other Earths reveals a profound truth. The universe is governed by the same set of physical laws everywhere. The gravity that holds us to the Earth is the same gravity that forges a black hole. The elements in our bodies, the carbon, the oxygen, the iron, were forged in the hearts of stars that died long ago. We are, in a very literal sense, made of stardust. Our search for life elsewhere and our study of cosmic monsters are two sides of the same coin. An exploration of our own cosmic origins. But as we peel back one layer of reality, we are confronted by an even deeper mystery. Everything we have talked about, the stars, the planets, the galaxies, the black holes, all the things we can see and touch and measure, all the normal matter, makes up only 5% of the known universe. The other 95% is a complete enigma, composed of two substances we have named but do not understand dark matter and dark energy. The first clue to this hidden reality came in the 1970s. From the work of astronomer Vera Rubin, she was studying the rotation of galaxies. She expected to see stars on the outer edges of a galaxy moving more slowly than the stars near the center. Just as the outer planets in our solar system move more slowly than the inner ones. But that is not what she found. The stars on the galactic fringe were moving just as fast as the ones further in. This defied the laws of physics. The only way this could be possible is if the galaxies contained far more mass and therefore more gravity than could be accounted for by the visible stars and gas. There had to be an enormous halo of invisible matter surrounding the galaxies, holding them together. We call this dark matter. It does not emit light. It does not reflect light. It does not interact with normal matter in any way we can detect, except through its gravitational pull. It is the invisible scaffolding upon which the visible universe is built. Without it, galaxies would have flown apart long ago. Stars, planets, and we would not exist. It makes up about 27% of the universe, and we have absolutely no idea what it is. And if that wasn't strange enough, there is the final, greatest mystery, dark energy. In the late 1990s, astronomers studying distant supernova made the most shocking discovery in modern cosmology. For decades, it was assumed the expansion of the universe, started by the Big Bang, was slowing down due to the gravitational pull of all the matter within it. The big question was whether it would slow down enough to eventually halt and recollapse, or just slow down forever. But the observations showed the exact opposite. The expansion of the universe is not slowing down, it's speeding up. Something is pushing the universe apart, working against gravity on the largest scales. A mysterious pressure inherent in the fabric of space itself. We call this dark energy, and it makes up a staggering 68% of the entire cosmos. It is a force we cannot explain, predicted by no existing theory, that dictates the ultimate fate of our universe. So, this is the state of our cosmic knowledge. We stand on a small rocky world, built from the ashes of dead stars, made of a type of matter that constitutes a mere 5% of the total cosmic inventory. We look out into the night and search for other worlds like our own, nestled in galaxies that are held together by an invisible form of matter we do not comprehend, all while the universe itself is being pushed apart by an unknown energy at an ever-increasing rate. Our most advanced instruments, like the James Webb Space Telescope, are our new eyes. They peer into the atmospheres of distant worlds, looking for the faintest traces of life. They gaze into the deepest reaches of space and time, capturing light from the very first galaxies to ever form, seeking to understand how the universe we know came to be. With every new discovery, every new planet identified, every new gravitational wave detected, we write another sentence in our cosmic story. But we are also reminded of how much of the book is yet unread. What other fundamental forces and particles are waiting to be discovered? Will we find that life, either simple or complex, has taken root on one of the trillions of worlds in our galaxy? Or will we find that our pale blue dot is, in fact, a miracle of profound rarity? The journey into the unknown continues. The light from distant stars and galaxies travels for eons to reach us, carrying with it the secrets of its origin. We have only just learned how to read its message. And as we look deeper, we can be certain of only one thing: the most astounding discoveries still lie ahead of us, waiting in the darkness. Yet, this darkness is not merely an absence of light. It is a canvas upon which the universe's most profound secrets are painted, and humanity, armed with ingenuity and insatiable curiosity, is learning to decipher its intricate patterns. The journey to understand our place, to grasp the full scope of the cosmic architecture, demands that we confront these enigmas head-on, not with fear, but with the relentless pursuit of knowledge. The hunt for dark matter, chasing the invisible scaffolding. The quest to understand dark matter represents one of the most intensive scientific endeavors of our time. Constituting roughly 27% of the universe, its gravitational influence is undeniable. Shaping galaxies and galaxy clusters, yet its fundamental nature remains elusive. How do scientists attempt to capture this ghostly substance? The primary strategy involves direct detection experiments. These are sophisticated, ultra-sensitive devices buried deep underground, in mines or beneath mountains, to shield them from the constant barrage of cosmic rays that would otherwise mimic a dark matter signal. The core principle is simple. If dark matter particles exist and occasionally interact with normal matter, then a sufficiently sensitive detector placed in a quiet enough environment might register the faint recoil of an atomic nucleus struck by a passing dark matter particle. Experiments like Lux Zeppelin LZ, located deep within the Sanford Underground Research Facility in South Dakota, USA, and Xenont in Italy's Gran Sasso Mountain, use massive tanks filled with ultra-pure liquid xenon. If a dark matter particle, a leading candidate, being the hypothetical WIMP weakly interacting massive particle, collides with a xenon nucleus, it should produce a tiny flash of light and a small charge signal. By detecting these faint signatures with photomultiplier tubes and sensitive electronics, scientists hope to identify the telltale fingerprint of dark matter. While no definitive detection has been made yet, these experiments continuously push the boundaries of sensitivity, ruling out vast swaths of possible WIMP properties and forcing theorists to refine their models. Another promising avenue focuses on a different candidate, the axion. Originally proposed to solve a puzzle in particle physics, the strong CP problem. Axions are incredibly light, weakly interacting particles that could also constitute dark matter. Experiments like the Axion Dark Matter Experiment ADMX at the University of Washington use powerful magnets within a resonant cavity. The theory predicts that axions passing through a strong magnetic field could convert into detectable microwave photons. ADMX scans different frequencies, listening for this faint signal, acting like a cosmic radio tuned to the axion channel. Like WIMP searches, this is a painstaking process, but it probes a completely different region of possible dark matter parameter space. Beyond direct detection, scientists also hunt for dark matter indirectly. If dark matter particles are their own antiparticles, a property predicted for some candidates like WIMPs, they could occasionally collide and annihilate each other, producing detectable radiation, particularly gamma rays. Space telescopes like NASA's Fermi Gamma Ray Space Telescope continuously scan the sky, looking for excess gamma ray emissions coming from regions where dark matter is expected to be dense, such as the center of our Milky Way galaxy or dwarf satellite galaxies orbiting the Milky Way. While intriguing signals have been seen, none can yet be definitively attributed to dark matter annihilation, as other astrophysical processes like pulsars or supernova remnants can also produce gamma rays. Gravitational lensing provides another powerful indirect method. As predicted by Einstein's general relativity, massive objects bend the path of light passing near them. Dark matter, despite being invisible, has mass and therefore exerts gravitational pull. By observing how the light from distant galaxies is distorted and magnified as it passes through massive galaxy clusters on its way to us, astronomers can map the distribution of all. The mass in the cluster, both the visible stars and gas and the invisible dark matter. Surveys like the Dark Energy Survey Day and the upcoming Vera C. Rubin Observatory will map the gravitational lensing effects across vast swaths of the sky, creating the most detailed 3D maps of dark matter ever made. These maps not only reveal where dark matter is, but also how it clumps and evolves over cosmic time, providing crucial clues to its nature and behavior. Dark energy, the cosmic accelerator, and the universe's fate. While dark matter pulls the universe together, dark energy pushes it apart. This mysterious force, making up a staggering 68% of the cosmos, is driving the accelerating expansion of the universe. Its discovery in the late 1990s, through observations of distant Type Ia supernova by two independent teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, was a profound shock. It overturned the long-held assumption that gravity would inevitably slow down the expansion following the Big Bang. Understanding dark energy is arguably the greatest challenge in fundamental physics today. What is it? Is it truly a constant energy density inherent to the vacuum of space itself, as described by Einstein's original cosmological constant lambda? Or is it something more dynamic, a field that changes over time, perhaps even evolving into a different form? The answer has staggering implications for the ultimate fate of everything. The Big Freeze heat death. Asterisk asterisk. If dark energy is a true cosmological constant lambda, the acceleration will continue indefinitely. Galaxies outside our local group will eventually recede faster than light, disappearing from view. Stars will burn out. Black holes will slowly evaporate via Hawking radiation over immense timescales. And the universe will become an increasingly cold, dark, dilute, and lifeless place. This is currently the most favored scenario based on existing data. The Big Rip, asterisk asterisk, if dark energy is not constant but increases over time, a form called phantom energy. Its repulsive force could eventually overcome all other forces. In this scenario, the accelerating expansion would tear apart galaxy clusters first, then galaxies themselves, then stars and planetary systems. And finally, in the last moments, it would rip apart atoms and even spacetime itself. This is a more dramatic, though less certain, possibility. The Big Crunch, asterisk asterisk. If dark energy were to weaken or reverse its effect over vast timescales, gravity could eventually regain the upper hand. The expansion would slow, halt, and then reverse. The universe would begin to collapse back in on itself, culminating in a cataclysmic reversal of the Big Bang, a Big Crunch. Current observations strongly disfavor this, as they show acceleration, not deceleration. The Big Freeze, heat death, asterisk asterisk. If dark energy is a true cosmological constant lambda, the acceleration will continue indefinitely. Galaxies outside our local group will eventually recede faster than light, disappearing from view. Stars will burn out. Black holes will slowly evaporate via Hawking radiation over immense timescales. And the universe will become an increasingly cold, dark, dilute, and lifeless place. This is currently the most favored scenario based on existing data. The Big Rip, asterisk asterisk. If dark energy is not constant but increases over time, a form called phantom energy, its repulsive force could eventually overcome all other forces. In this scenario, the accelerating expansion would tear apart galaxy clusters first, then galaxies themselves, then stars and planetary systems. And finally, in the last moments, it would rip apart atoms and even spacetime itself. This is a more dramatic, though less certain, possibility. The Big Crunch, asterisk asterisk. If dark energy were to weaken or reverse its effect over vast timescales. Gravity could eventually regain the upper hand. The expansion would slow, halt, and then reverse. The universe would begin to collapse back in on itself, culminating in a cataclysmic reversal of the Big Bang, a big crunch. Current observations strongly disfavor this, as they show acceleration, not deceleration. To distinguish between these possibilities and understand dark energy's nature, astronomers are conducting massive cosmic surveys. The Dark Energy Spectroscopic Instrument, DESI, mounted on the Nicholas U. Mayall telescope at Kitt Peak National Observatory, is creating the largest 3D map of the universe ever constructed. By measuring the precise positions and distances via redshifts of tens of millions of galaxies and quasars, DESI traces how cosmic structures have grown and how the expansion rate has changed over billions of years. This detailed history provides powerful constraints on dark energy models. Space missions are also crucial. The European Space Agency's Euclid satellite, launched in 2023, is mapping the geometry of the universe with unprecedented precision. It will measure the shapes of over 1 billion galaxies to study weak gravitational lensing, caused by both dark matter and dark energy, and measure the clustering of galaxies to chart the expansion history. Its primary goal is to understand whether dark energy is consistent with a cosmological constant or requires a more complex explanation. Looking ahead, NASA's Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will be a game-changer. With its enormous field of view, 100 times larger than Hubble's, Roman will conduct massive surveys, discovering thousands of Type Ia supernova and measuring the shapes and distances of billions of galaxies. This vast dataset will allow astronomers to test dark energy theories with extraordinary precision, potentially revealing whether it evolves over time and providing clues to its fundamental origin. Multi-messenger astronomy, hearing the universe's symphony. The revolution in astronomy isn't just about seeing farther. It's about perceiving the universe through entirely new senses. We are entering the era of multi-messenger astronomy, where cosmic events are studied not just through light photons across the electromagnetic spectrum, but also through gravitational waves, neutrinos, and cosmic rays. Each messenger carries unique information about the universe's most violent and energetic phenomena. The detection of gravitational waves by LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo in 2015 marked the dawn of this new era. These ripples in spacetime itself, predicted by Einstein a century earlier, are generated by cataclysmic events involving massive, compact objects, colliding black holes, merging neutron stars, and potentially even the Big Bang. Each detection provides a direct probe of gravity in its most extreme regime and reveals properties of the colliding objects impossible to glean from light alone. The 2017 detection of gravitational waves from the collision of two neutron stars, GW170817, was a landmark. For the first time, astronomers observed the same event through both gravitational waves and electromagnetic radiation, gamma rays, X-rays, ultraviolet, optical, infrared, and radio waves. This confirmed that neutron star mergers are cosmic forges, creating heavy elements like gold, platinum, and uranium, and solving a long-standing mystery about the origin of these elements in the universe. Neutrinos ***, often called ghost particles, offer another unique window. Produced abundantly in nuclear reactions within stars, during supernova explosions, and potentially by dark matter annihilation. Neutrinos interact so weakly with matter that they travel almost unimpeded across the cosmos. Detectors like IceCube, buried deep within the Antarctic ice, use a cubic kilometer of ultra-clear ice as a target. When a high-energy neutrino rarely collides with an ice molecule, it produces a flash of blue light detected by sensitive photomultiplier tubes. IceCube has detected astrophysical neutrinos originating from outside our solar system, including some likely coming from active galactic nuclei powered by supermassive black holes. Future neutrino telescopes, like the proposed KM3NET in the Mediterranean Sea, will be even more sensitive, potentially pinpointing neutrino sources and revealing the engines powering the most energetic cosmic accelerators. Cosmic rays ***, high-energy atomic nuclei, mostly protons, and electrons raining down on Earth from space, provide yet another messenger. While their paths are scrambled by magnetic fields, the highest energy cosmic rays travel in relatively straight lines, potentially pointing back to their sources. Observatories like the Pierre Auger Observatory in Argentina and the Telescope Array in Utah cover vast areas to detect the extensive air showers created when these ultra-high energy particles slam into Earth's atmosphere, identifying the sources of these particles, which can carry energies millions of times greater than what human-made accelerators can achieve, remains a major goal, potentially revealing exotic astrophysical objects or new particle physics. By combining data from all these messengers, light, gravitational waves, neutrinos, and cosmic rays, astronomers can build a far more complete and nuanced picture of cosmic events. This multi-pronged approach is essential for understanding phenomena like black hole formation and growth, the inner workings of supernova, the behavior of matter under extreme conditions, and the nature of dark matter and dark energy. Each messenger provides complementary information, like different instruments in a cosmic orchestra, revealing the symphony of the universe in unprecedented detail. The search for life, new eyes on distant worlds while grappling with the universe's largest components. The search for life beyond Earth remains one of humanity's most compelling quests. The James Webb Space Telescope JWST is just the beginning of a new generation of instruments designed to scrutinize exoplanets for signs of habitability and, potentially, life itself. Future space telescopes will be even more powerful. Concepts like the Large UV, Optical, IR Surveyor Lavoir, and the Habitable Exoplanet Observatory HABOX envision telescopes with primary mirrors. Ground-based telescopes are also undergoing a revolution. The extremely large telescope ELT, currently under construction in Chile's Atacama Desert, will boast a 39-meter primary mirror, making it the largest optical near-infrared telescope in the world. The Giant Magellan Telescope GMT and the 30-meter Telescope TMT are also massive projects underway. These telescopes, equipped with advanced adaptive optic systems to correct for atmospheric blurring, will be powerful enough to directly image larger exoplanets and study the atmospheres of smaller, potentially rocky worlds in transit. They will complement space telescopes by providing higher resolution imaging and spectroscopy for brighter targets, helping to identify the most promising candidates for future detailed study by space missions like Lavoir. The search isn't confined to distant stars. Within our own solar system, several missions aim to explore potentially habitable environments. NASA's Europa Clipper, scheduled for launch in October 2024, will perform dozens of close flybys of Jupiter's moon Europa. It carries a sophisticated suite of instruments to characterize the moon's ice shell thickness, map the subsurface ocean, measure the salinity of any water plumes erupting from the surface, and assess the habitability of this hidden ocean. Clipper won't land, but it will pave the way for a future lander mission that could search directly for signs of life within Europa's ocean. Similarly, Dragonfly, a NASA mission scheduled for launch in 2027, is a rotorcraft lander designed to explore Saturn's moon Titan. Titan is unique in having a thick atmosphere and stable liquid on its surface, not water, but methane and ethane lakes and rivers. Dragonfly will fly to dozens of locations across Titan's diverse surface, sampling the complex organic chemistry in its atmosphere and on the ground. Titan's prebiotic chemistry, driven by solar energy and possibly internal heat, offers a natural laboratory to study chemical processes that might have led to the origin of life on Earth, even if life doesn't currently exist there. Mars remains a key target. While the Perseverance rover is currently collecting core samples in Jezero crater to be returned to Earth by a future Mars sample return campaign. Future missions aim to explore other, potentially habitable niches. Concepts for missions to explore Martian subsurface caves, where liquid water might still exist, or to drill deep into the subsurface ice, are being actively studied. Finding definitive evidence of past or present microbial life on Mars would be one of the most profound discoveries in human history. Pushing the boundaries, interstellar probes and the future of exploration looking further ahead. Visionary projects aim to extend our reach beyond the solar system. Breakthrough Starshot, an ambitious initiative funded by the Breakthrough Prize Foundation, proposes sending tiny, gram-scale spacecraft starships to our nearest stellar neighbor, the Alpha Centauri system, just over 4 light-years away. The concept involves propelling these miniature probes, equipped with cameras, sensors, and communication systems, to 20% the speed of light, using powerful ground-based laser arrays pushing on lightweight light sails. While the technological challenges are immense, developing the lasers, the sails, the micro-spacecraft, and the communication system over interstellar distances. Starshot represents the first serious attempt to develop technology for interstellar travel. If successful, a flyby mission could return images and data from Proxima Centauri b, the potentially rocky planet orbiting Proxima Centauri, within decades of launch. Closer to home, the Vera C. Rubin Observatory, formerly LSST, nearing completion in Chile, will revolutionize our view of the dynamic sky. With its 8.4-meter mirror and massive 3.2 gigapixel camera, Rubin will scan the entire visible southern sky every few nights for 10 years. This unprecedented cadence and sensitivity will discover millions of supernova for dark energy studies, map billions of galaxies for dark matter distribution, identify tens of thousands of Kuiper belt objects and potentially hazardous asteroids, and detect countless transient events, from variable stars to gravitational wave counterparts. Rubin will essentially create a 10-year, high-resolution movie of the southern sky, revealing the universe's behavior on timescales from seconds to years. The square-kilometer array sky, currently under construction in Australia and South Africa, will be the world's largest radio telescope when completed. Comprising thousands of antennas spread across continents, the SKA will have a total collecting area of 1 square kilometer. Its incredible sensitivity and resolution will allow it to detect the faint radio signals from the epoch of reionization, the era when the first stars and galaxies lit up, ending the cosmic dark ages just a few hundred million years after the Big Bang, asterisk. Map the distribution of hydrogen gas throughout cosmic history with unprecedented detail. Discover and precisely time thousands of new pulsars, using them as cosmic clocks, to test Einstein's general relativity in extreme gravity and potentially detect low-frequency gravitational waves from supermassive black hole mergers, search for complex organic molecules in protoplanetary disks, the birthplaces of planets, potentially detect technosignatures, evidence of technological activity from other civilizations. Looking further into the future, space-based gravitational wave observatories like the Laser Interferometer Space Antenna LISA will open a new window onto the low-frequency gravitational wave universe. LISA, a planned ESA NASA mission, will consist of 3 spacecraft flying in a triangular formation, separated by millions of kilometers. Lasers bouncing between the spacecraft will measure tiny changes in their distances caused by passing gravitational waves. LISA will be sensitive to much lower frequencies than LIGO Virgo, allowing it to detect the mergers of supermassive black holes, millions to billions of solar masses at the centers of galaxies, events that are invisible to current ground-based detectors. The inspiral and merger of stellar mass compact objects, like white dwarfs or neutron stars, into supermassive black holes in galactic centers, providing probes of extreme gravity, a stochastic background of gravitational waves, potentially generated by cosmic inflation or cosmic strings in the very early universe. The cosmic perspective, our place in the grand narrative. As we develop these incredible tools and make these profound discoveries, we continually refine our understanding of our place in the cosmos. The universe, we've learned, is governed by the same physical laws everywhere. The gravity that holds us to Earth is the same gravity that sculpts galaxies and forges black holes. The elements in our bodies, carbon, oxygen, nitrogen, iron, were forged in the nuclear furnaces of massive stars that lived and died billions of years ago. As Carl Sagan famously said, "We are made of star stuff. This cosmic connection is not poetic. It's a fundamental, verifiable truth revealed by astrophysics. Our exploration of dark matter and dark energy, our search for exoplanets and life, our study of black holes and the early universe, these are not separate endeavors. They are interconnected facets of the same grand quest to understand our origins, our nature, and our future. Each discovery reshapes our perspective. Finding that planets are common, that the basic building blocks of life exist in interstellar space and on other worlds, that galaxies are embedded in invisible halos of dark matter, that the universe's expansion is accelerating. All these revelations force us to confront the scale, complexity, and inherent mystery of existence. The knowledge that 95% of the universe is composed of substances we fundamentally don't understand is humbling. It reminds us that for all our progress, we are still standing at the threshold of cosmic understanding. Yet, this humility is coupled with an extraordinary sense of possibility. The tools we are building, Rubin SKA, ELT, Roman, Lavoir, Lisa, and others yet undreamed of, are our keys to unlocking these deepest secrets. They represent the collective ambition of humanity to comprehend our reality. The journey into the unknown continues. Every photon captured by a distant telescope, every gravitational wave ripple detected, every neutrino recorded, every exoplanet atmosphere analyzed, every piece of dark matter mapped, each adds a new sentence, a new paragraph, to the grand cosmic narrative. We are the universe becoming conscious of itself. We are the means by which the cosmos, after 13.8 billion years of evolution, can look back and wonder at its own existence, its own structure, its own invisible architecture. The darkness between the stars is no longer an empty void. It is a tapestry woven with dark matter, threaded with dark energy, and illuminated by the light of distant suns and the echoes of cosmic cataclysms. It is a landscape of profound mystery and breathtaking beauty. And we, the curious inhabitants of a small, rocky world orbiting an ordinary star in the outskirts of a vast galaxy, have only just begun to learn how to read its story. The most astounding chapters, we can be certain, are still waiting to be written. Hidden in the depths of space and time, waiting in the darkness, for us to find them